Have you ever tried to get a video AI to do something that sounds super simple, like make the triangle go right and the square go down? Turns out that's one of the biggest challenges for even our most powerful models today. Well, we're diving into a new model called Action Party that might have finally cracked this code. And it's all about teaching AI how to play together.
Okay, so let's just see this in action. Because the difference is, wow, on the left, you see what happens with a standard top-of-the-line video model. You give it simple, clear commands, and you get this chaotic mess. The model has no idea which shape is supposed to do what. But then look at the right. That's Action Party. The triangle moves right, then the square moves down. Every action is perfectly tied to the right character. It's truly night and day.
So this just begs the question, right? Why is this so incredibly hard? I mean, these are generative models that can create stunning, photorealistic worlds from scratch. Why do they just fall apart when you ask them to control two simple shapes at the same time? Well, the answer has a name. Researchers call it the action binding problem. And it's exactly what it sounds like. When the model gets multiple instructions, like triangle moves right and square moves up, it just can't correctly bind the action to the subject. It hears all the words, but it gets them all jumbled up. It's like it knows what to do, but has no idea who is supposed to do it.
So how in the world did the team behind Action Party solve this? Well, the big breakthrough came when they stopped thinking like a filmmaker and started thinking more like a video game developer.
And this is the absolute core of the idea. Instead of just trying to paint the next frame of a video, Action Party acts like a generative game engine. It treats the whole scene as a simulation, complete with persistent characters that have their own stats and follow a set of rules, just like in a video game.
To pull this off, they introduced something totally new called subject state tokens. You can kind of think of these as a unique digital ID, or maybe like an invisible name tag for every single character in the scene. And this token isn't just a name, it's constantly tracking the character's state. Most importantly, its exact 2D coordinates on the screen from one frame to the very next.
So this whole game engine approach really just boils down to a super simple two-step loop. It's beautiful. First, the model looks at the action command for a character, and it updates that character's state token with its new position. Step 2, once all the new character states are figured out, the model just renders the final video frame, drawing every character in its new spot. Update, then render. It's logical, it's structured, and as we'll see, it really works.
All right, so let's pop the hood and see how this thing actually works. What are the mechanisms that make this game engine tick? Well, the secret sauce really comes down to two super clever tricks, something called attention masks and a really cool technique for spatial awareness called rope biasing. Let's break them down. Okay, let's tackle that first step, updating the character states. So you've got a list of actions, move left, move right, and you've got a list of character IDs, right? Those state tokens. How do you make absolutely sure that move left talks only to the blue square's ID and move right talks only to the red triangle's ID with zero confusion? The solution is just so elegant, and this visualizes it perfectly. Think of it as the rulebook. What you're seeing here is a cross-attention mask. It's basically a set of rules that creates a private one-to-one communication channel between each action and its specific character token. The mask literally tells the model, hey, the command for the triangle is only for the triangle's ID. All the other lines of communication are just blocked. It completely prevents any crosstalk or mix-ups.
Okay, so the state is updated. The model knows abstractly that the blue square's ID should now be at coordinates, say, 50 by 100. But how does it find the actual pixels of the blue square in the last frame to know what it needs to redraw in that new spot? Remember, the state token is just an ID, it's not a visual object.
The researchers themselves put this challenge perfectly. How can you connect these abstract control signals, these ideas, with characters that only exist as a bunch of colored pixels in an image?
And the answer, which is just brilliantly shown here, is something we can call this spotlight. The tech behind it is called rotary position embeddings, or ROPE for short. And what it does is it basically creates a spatial bias. It shines a spotlight on each character's location in the video frame, anchoring its abstract state token to its visual self. It tells the model, hey, the character with ID number 2, it's right here in the image. This is where you need to apply the update.
So, the theory is fantastic. The architecture is really clever, but the real question, the one that always matters, is does it actually work in the real world? Let's take a look at the results. So,
Action Party wasn't just tested on some simple little demo. Oh no, it was put through the ringer on something called the Melting Pot Benchmark. And this thing is a tough test. It's a collection of 46 different, really complex 2D multiplayer games that are designed specifically to challenge multi-agent AI.
And the results are, well, they're just staggering. Take a look at this graph. See that green line shooting up and staying at the top? That's Action Party. It maintains an incredibly high accuracy over time. Now look at the red and purple lines huddled at the bottom. Those are the other advanced models. Their performance just completely collapses. It goes to almost zero, almost immediately. This isn't just a small improvement. This is a whole other level of performance.
So how far can it push this? The model can successfully and simultaneously control up to 7 different characters in a single scene. That's 7 independent agents, all following their own unique commands all at the same time.
And as you can see here, that control holds up across a huge range of different situations. Action Party is remarkably versatile. This is not a one-trick pony. We're seeing it work flawlessly in totally different game environments, from cooperative cooking games to chaotic chemistry simulations to complex predator-prey scenarios. The core ideas just generalize beautifully.
Now, a good scientist always has to ask, okay, but did we really need all of that? What happens if we start taking pieces out? Is the rulebook mask or the spotlight bias really that essential?
Well, this slide gives us the visual proof. Top left, you've got the goal, the ground truth, and right next to it, the full Action Party model, tracking it perfectly. But then look at the others. The second you remove either the attention mask or the rope bias, it's a catastrophic failure. The control is just completely gone. It's chaos all over again. And the numbers here just confirm what our eyes are telling us. With the full system, you're getting over 87% accuracy. You take away the rope spotlight, and it plummets to 3.2%. You take away the cross-attention rulebook, and it drops to 5.2%. This proves without a doubt that every single piece of this architecture is absolutely critical for its success. So it's pretty clear Action Party is a game changer for creating controllable AI inside virtual worlds. But what does solving this action binding problem really mean for the rest of us? The implications go way, way beyond just gaming.
The reason this really matters is because it unlocks the door to some seriously complex multi-agent simulations. We're talking about training swarms of robots to work together on a task, or creating hyper-realistic traffic simulations to test self-driving cars in millions of different scenarios, or even building entire interactive worlds for research and discovery. This is a fundamental building block for the next generation of AI.
Which really just leaves us with one final, pretty exciting thought. For the first time, we've given AI a robust way to truly play together, to share a space while following their own individual goals. So the big question now is, if they can learn to play together, what incredible new worlds can they learn to build together?